quickly jog your memory about work, energy, and power. And we talked about work in our first area of study, and we looked at some different examples of when work was and wasn't being done. And we talked about the fact that the word work, colloquially, you might think of, exerting energy or effort, but in a physics formal definition, it means that you are exerting a force on an object, and that force is causing a displacement either parallel or anti-parallel to that object's displacement. So we talked about some examples here, and these two that I've ticked are ones where work is being done. Book falling off a table and free falling to the ground, force due to gravity is doing work, causing a displacement of that object from the table to the ground. Rocket accelerating through space is very similar. Force pushing the rocket forward, causing a forwards displacement. The fifth example here, the ball on the end of the string, yes, a force is being applied, but remember when we've got something traveling in a circle, the force is always towards the center of the circle. That would be 90 degrees to the displacement. At this moment here, the velocity is in this direction, so that's the direction it will be traveling. So force and velocity at 90-degree angles means that there's no work being done. We looked at a couple of ways that we can calculate work. Oh, before we do that though, I do need to mention work could also hinder displacement. So friction can do, in quotation marks, negative work where an object loses energy. That's an option as well. If we had a box sliding along the ground in this direction, that was its velocity, and the friction was acting to oppose that, the friction is changing this object's displacement by slowing it down. So that's also a work situation, but it's causing that object to lose kinetic energy, and that might be dissipated in the form of heat. So going back to what I was saying, calculating work, there are two ways dependent on the kind of force that is acting. If we've got a constant force, then we just take that force, we multiply it by that displacement, and if that force is at an angle, then we did that cosine of the angle. If we had a non-constant force, we had to look at the force displacement graph, and the work was the area underneath the graph. In either case, when you're calculating work, the unit is joules. Remember, work was defined as something that caused a change in energy. So we previously did a little bit of this, work equals delta E. So if work is a change in energy, then the units have got to be the same as the units of energy, which is joules. It's also defined as the work done when a force of 1 Newton acts through a distance of 1 meter. That's handy to know. So power is actually the rate of doing work. Average power is the total work done divided by the total time. You might write this as P equals W for work over delta T. I tend to just write it as W over T because I'm lazy. Now, it can also be found using a different method. So let's put what we just talked about here. Work divided by time gives us power. If we had a constant force, work was equal to Fs. Let's say we're dealing with a situation where there's no angle that's needed here. So Fs, let's say it's a constant force situation. Replace W with Fs, let's put that over T again. You might recall that displacement over time gives you velocity. So we could replace that with Fv. Power is a scalar quantity, so it has units of joules per second, or we could just replace that with watts, which is capital W. Be careful, that is a unit. It is not the same as the symbol that we have to represent work. Work, symbol W, has units of joules, whereas power, we use capital P, and that has the units of watts. They're two different things. Don't confuse power, capital P, with momentum, lowercase p. So some types of energy that we've looked at in this course so far. Kinetic energy is one. You might like to write that as E subscript K. I've sometimes used KE in the past as a shortening. And remember, that's the energy associated with the motion of an object. So that's half mv squared. The next kind of energy we talked about was gravitational potential energy. That can be represented as Eg. I've also used GPE. And in a question we're going to look at in a moment, they've used capital U subscript G. U often talking about potential energy, a weird convention they've got in physics. We define that as the energy associated with something being a certain height above something. And in the cases we've dealt with, we've been using MGH. Another kind of energy, spring potential energy, also known as strain potential energy or elastic potential energy. You need to be comfortable with those three different wordings for that. I tend to use E subscript S. We haven't looked at this yet, but we will in future. It's actually equal to a half K and then times delta X squared. I like to put the delta X in brackets just to ensure there's no confusion there. We've also talked about work being done. We talked about that literally moments ago, due to friction. So if we had an example where we had a constant friction being applied to an object over a displacement, we would just calculate the work done due to friction as the friction times that displacement. So these are the four main kinds of energy that we look at. Yes, there are also things like chemical energy and energy associated with nuclear stuff, but that's not really what we're going to be looking at here. We can also look at energy efficiency. Now, as a reminder, energy is never lost. It's merely converted into another form. So it's not technically correct to say energy is lost. You need to be a little more specific. You might talk about kinetic energy being lost, but that kinetic energy needs to go somewhere. Perhaps it's being turned into heat. So work done due to friction is causing that energy to be dissipated as thermal energy. So remember, talk about the type of energy and its location. That's what this little exam tip box is here. So that being said, useful energy, we can talk about some energy being converted into unhelpful energy. For example, energy dissipated as thermal energy. If you're talking about, I don't know, a break on a bike tire, that heat that's caused there is not helpful. We can't do anything with that other than possibly burn our hands if we accidentally touch it. So that's an unhelpful kind of energy in that particular circumstance. Sure, there are other examples where we want heat to be created, like a hairdryer or a little electric heater, but that's a different kind of thing. So if we're doing percentage efficiency calculations, you're going to have some final energy. So perhaps you've got some system where you've got 75 joules out, as an example. If you had a useful energy of 75 joules out, but perhaps you actually put 100 joules of energy in, you would do the useful energy divided by the initial energy times by 100 to get that as a percentage calculation. So in this particular example, with the numbers I've used, it would be 75% efficient. Okay, let's look at an example here. I altered this question, but I realized that the numbers I chose weren't very good. So can you please alter it to a mass of 0.05 kilograms is released from a height of 10 meters above the surface of Earth? We're going to be ignoring air resistance. We're told we want to sketch the gravitational potential energy of the mass as a function of the height above the surface of Earth on the axis provided below. We want to label the potential energy as UG, so U subscript G. Take the potential energy at the surface of the Earth to be 0, sure. Include the initial potential energy value on the energy axis. On the same axes, sketch the kinetic energy of the mass and label this as EK. Alrighty. So I guess we need to figure out a first point to be able to put on here. Okay, just in case sig figs freak you out, I've changed that to 0.050 kilograms. So let's do a first point. The mass we've got, G, we're on the surface of the Earth, so we can safely use 9.8. And the initial height is 10. So this gives us 4.9 joules. So we need to plot that. Let's get our pencil ready to go. 4.9. Now this height is 10. So we need to do it a smidgen under 5 there. I know, now there's a couple of ways you could do this question. I know when we get to a height of 0, we're going to have an energy of 0. So I've just put a point down here. Now I know this is going to be linear, because I know UG is proportional to H. But if you didn't trust me, you could do a series of calculations here. You could do UG for each different height, but I think that would actually be inefficient. So I know it's going to be a straight line, but let's maybe figure out when the height is 5 what the point is, just to convince you. So if we're ignoring sig figs, because we're just caring about putting dots on a graph here, that would be 2.45 joules, which is half the value we originally had. So if you really weren't convinced that UG was proportional here, you could go ahead and sub in some more value. If you just put some numbers in your calculator and just change the value of the height here, you could get the values really quickly, or you could recognize that it is a linear relationship. So let's get our ruler. So we need to label this, very important, U subscript G. So the potential energy is proportional to the height. With this example, when we're at the top here, we're told this object was released from a height. that's implying that the initial velocity is equal to 0, and that implies that the kinetic energy is equal to 0. So that means this here, at this point here, the total energy this object has is told by this point. It has UG of 4.9, and the kinetic energy is 0. So the total energy is always going to be equal to 4.9. Why is that helpful to know? Well, we need to draw a kinetic energy graph. So let's look at this last point here. We said that UG was equal to 0, so that means all of that energy must have been converted to kinetic energy. So the kinetic energy must be 4.9 joules here. There's no air resistance, there's no other energy form here because there's no spring, so all of that initial potential energy must have been converted to kinetic. So that means our kinetic energy graph is going to have a 4.9 here, and go down to 0 here, and also be linear. Very nice. Okay, we've got a delivery van, has this mass and this initial velocity colliding with the pole. The impact crushes the crumple zone. So important to have crumple zones. Please review the video about minimizing an impact force if you don't recall why. Crumples it by 0.60 meters and it brings the van to rest. Now my initial instinct was to do F delta T equals m delta v. The reason is we've used that for impacts before. That could calculate the average force. We've got the different velocities, we've got the mass, but unfortunately we don't have the time. So there's two ways I guess we could do this now. We could use, oh no, the force will be variable. So I was thinking, could we use suvat to figure out, using that displacement, what the time would be, but it's a variable force here, and we'll be calculating an average force later, so perhaps that could work, but I think I'd be more comfortable using an energy approach for this. So because I know work is force times displacement, and I also know it's a change in energy, let's figure out the change in kinetic energy here, and that kinetic energy is being lost, but it's being converted to work done to deform this material, to crumple that crumple zone. So let's calculate that change in energy. So that's going to be the change in kinetic energy. So the initial kinetic energy, the final kinetic energy minus the initial. So if we do the final kinetic energy is half mv squared, and we do minus half mu squared. So looking at the question again, we're told the initial velocity was 20 meters per second, but the final velocity was brought to rest, so v equals 0. So that means this goes away, so the change in energy for this object is a minus half mu squared. It's a minus because that object is losing kinetic energy. Now that loss in kinetic energy is going to be transformed into the work done, as I said, to crumple that crumple zone. So we don't really care about the negative, it's just indicating that kinetic energy is being lost. So if you wanted to ignore it, you can. I'm going to keep it in for this step, but then translate it to the other step. So minus a half times the mass times u squared. So 2.4 by 10 to the 5 joules. I hope I did that right, 4 or 5, yep. So that kinetic energy is being transformed into work done to crumple that zone. So if work equals Fs, then that force is going to be the work divided by S. And like we said, the change in energy was equal to the work. I did forget that negative sign there, but we don't need it for this. So the work done was the change in energy, and we just care about it being 2.4 by 10 to the 5. That displacement was 0.60 meters. So I get 4.0 by 10 to the 5 newtons. That is a very large force. Okay, let's look at this 1981 question now. Box of 20 kilos is pulled 3 meters along a rough floor with a force of 100 newtons, that's here. Friction force acting on the box is a constant 30 newtons. What is the change in kinetic energy of the box? Okay, to be able to do this, we care about the net force on this box. The net force will be 70 newtons acting in this direction. That force has the same effect on this box. It doesn't matter that it's 100 newtons and 30 newtons. We only care about the net force. So what is the change in kinetic energy of the box? Like we talked about previously, the change in kinetic energy is equal to the work done, and we can figure out the work done by knowing the force times the displacement. The displacement we were told in the question. So delta E equals force times displacement. There's no, that delta E is just going to be the kinetic energy because there's no gravitational potential energy, there's no spring potential energy. We've already accounted for that frictional force. Okay, good. Change in kinetic energy is going to be the force, net force of 70 times the displacement. So that should technically be 2.1 by 10 to the 212 joules. Now we're told the same mass is transferred to a frictionless table. The 100 Newton force is applied 20 degrees to the horizontal. So we have no more friction. We've got this force acting at 20 degrees to this horizontal line. Calculate the work done on the box as it's dragged 3 meters. So this is an example where we'd need to use the Fs cos theta. So it's just 100 newtons acting now, times, we're told, same displacement, 3.0. We need to do times that cos of 20. Alrighty, so popping that into my calculator and doing it to 2 sig figs. So 2.8 by 10 to the 2 newtons. Question from my brain. I don't remember writing that. We have a nice new question here. In a braking test, we've got a car of mass 1,000 kilos. It's travelling down a hill on a straight road, so no circular motion. Car's travelling at 20 meters per second. Let's call that U, or you could call that V subscript A. I don't mind. And we're told there's a constant braking force. So we've got some braking force, let's call it FB, which is constant. That's handy. That means if we're doing work calculations, we could just do that constant braking force times the displacement, rather than needing a force displacement graph in the area underneath. We're told that the car comes to a stop at B, 100 meters from A. Okay, so here's point B. And we're told 100 meters is this linear distance the car's going through. So, I'm not sure what the first question is asking. I'm pretending I'm not looking at this for the moment. Let's imagine the kinds of energies that are going on here. At the top, it's got gravitational potential energy because it's 10 meters above the ground. And we'll call this the zero height point. So it's got gravitational potential energy and it's got kinetic energy because it's traveling at a speed, EK. If we added those together, because there's no spring potential and there's no other energies acting here, that would give us the total energy. Let's look at this point down here. It's at a height of 0, so it's got no gravitational potential energy. We're told that it's brought to a stop here. So that means, unlike a lot of the roller coaster questions we've dealt with in the past, there's no kinetic energy. So that means all of the energy has been transformed in the work done by that brake. Very nice. So that means all of the energy has been converted to that. Now, where did that energy go? Like we talked about previously with that bicycle brake, it gets very hot. Maybe it's emitting a sound. That's another energy we can look at. So that energy is not disappearing into nowhere. It's being converted to sound, heat, stuff like that. Okay, the first question. What is the kinetic energy of the car at A? Oh, easy peasy. At A, the kinetic energy is just going to be equal to a half m, let's call it u squared. If you said v squared, I don't mind. So half times the mass was 1,000 times, we were told it was going 20. Nice easy starter into this question. Okay, so I get 2.0 by 10 to the 5 joules. That's not the total energy here. The question doesn't ask for it, but if we wanted to find the total energy, we'd also need to find the gravitational potential energy at this point. Oh, interesting. The next question is prompting us to do that. It is saying, what is the change in gravitational potential energy of the car going from A to B? Well, if we're interested in the change in gravitational potential energy, that would be the final mg, we'll put height at B, because it goes from A to B, it's finally at B, minus mgha. So that's the initial at point A. We said previously that there's no gravitational potential energy at point B. So that means it's losing gravitational potential energy. So we've got minus mgha. That minus is merely indicating that when we go from point A to point B, gravitational potential energy is lost. If we're calculating the total energy later on, we'd just be interested in, here for example, the positive value of that energy. So we need to calculate that. The mass was 1,000. We're near the surface, 9.8, and the height at A was 10 meters. So this is one of those nice old questions where G would have normally been 10, but that's okay. We're going to put 9.8 by 10 to the, 1, 2, 3, 4 joules lost. I'm not going to put a negative, I'm just going to represent that with the lost. I should technically say converted. Converted to other energies. Okay, now we're asked to find the magnitude of the constant braking force acting on the car when it's moved from A to B. So what we need to do here, the total energy at A is going to be equal to the total energy at B. So at A, what kinds of energies do we say it had? It had the gravitational potential energy and it had the kinetic energy. Oh, now conveniently we've already calculated those. So the kinetic energy plus the gravitational potential. If it loses 9.8 by 10 to the 4 joules going from A to B, it must mean it had 9.8 by 10 to the 4 joules of gravitational potential energy at point A. Now the total energy at B, we said there's no gravitational, there's no kinetic, it must all be that work done. So if you didn't want to do this step and you wanted to go straight to the next one with half mv squared plus mgh equals work, it's a constant force, force times the displacement, you could do that. But we previously calculated these things, so I'm just going to shove in the values. So kinetic energy was 2.0 by 10 to the, I've already forgotten, 5. And the gravitational was 9.8 by 10 to the 4. Pretty confident with that. Don't think I made a calculation error, but if I have, let me know. So instead of work, let's write the force times the displacement. You could have even done that here. And we know the displacement is 100 meters. So I'm going to pop that in there. Okay, do some algebra, see if you get the same thing I get. Okay, I hope I got this right. I got 2980. We do need to go to 2 sig figs though, so 3.0 by 10 to the 3 newtons. So just a reminder with our kinds of energy. We talked about kinetic energy, gravitational potential energy, spring, strain, or elastic potential energy, and possible work done, often due to friction, but in this example it was a braking force. And remember, the total energy, the amount of water in those cups remains the same, but it might just travel into different cups. We can't throw water out though, it needs to be in one of those places. So in this particular example, we started off with kinetic and gravitational potential energy, but by the time, by the time this object was at the bottom of the track, all of that energy was converted to that work done due to that braking force.